Hello students, good morning. So we begin with our today's session. We are looking into serial peripheral of 8051 microcontroller. In the last lecture, we started with serial peripheral. 8051 microcontroller provides one serial peripheral circuitry, and it is of what type? It is full duplex UART communication, universal asynchronous reception and transmission. That is, the transmission and reception can happen simultaneously on those two pins TXD and RXD, that is P3.1 and P3.0 of microcontroller. Okay. Then we looked into whenever we perform UART communication, this is how is that UART frame. The 8 data bits transmitted are packed in between the start and the stop bit. Okay, either you can have an 8-bit data or you can have a 9-bit data which can be transmitted one by one. So the start bit is transmitted first, then the D0 bit, then the D1 bit, and the so on up to D7 bit, right? So such one by one the bits are transmitted on TXD pin and are received on the RXD pin of the receiver. Fine, this is what we had seen in the last lecture. And then we looked into the special function registers associated with serial communication. One is SCON, serial control register, and the other one is SBUF. Serial control register, SCON, right? It is bit as well as byte accessible. What control does it do? Start and stop of the communication, whether the communication should be of 8 data bits or 9 data bits, and in which mode should be the communication. So these features are controlled by SCON register. And the data which is to be transmitted or received is stored in SBUF. It's a storage register. Then we saw that SCON register in detail. Whether the reception is completed or not is received in the RI bit, that is SCON.0 bit. RI stands for receiver interrupt. If the bit is 1, mean the reception is completed. 0 mean microcontroller is still receiving the data bytes one by one. TI, that is transmitter interrupt. If TI is 1, mean the transmission is completed. TI 0, the transmission is still going on. If we are going to perform 9-bit communication, then the 9th bit is stored in the SCON register. RB8 is receiving the 9th bit, and TB8 we will be storing the 9th bit which is to be transmitted. Whereas the 8 data bits will be stored in SBUF. The next is REN, receiver enable. Whenever REN bit is 1, reception begins. REN is 0 mean the reception is disabled. Whereas in case of transmission, any character, whenever it is loaded in SBUF, automatically the transmission begins. Okay, so SCON register provides 1 bit for reception, whether it is to be enabled or disabled, right? Then the next are the mode control bits. SM2 is used during multiprocessor communication, and SM0, SM1 are the 4 mode control bits. And we looked into the 4 4 modes of serial communication. 00 mode 0, it is synchronous serial communication, right? It is operating as a shift register with a frequency f oscillator by 12. 01 is mode 1, 8-bit UART communication with a variable baud rate. 10 mode 2, 9-bit UART communication with 2 fixed baud rate, f oscillator divided by 12 and f oscillator divided by 32. And 11, which is mode 3, is a 9-bit UART with a variable baud rate. And then we ended up with looking into the formula for baud rate, right? Baud rate is how many bits are sent in a second, is how a baud rate is defined. Is that okay? So 9600, if for example we have 9600 baud rate, it means 9600 bits are sent in 1 second. This is what it means. Okay. If you look into the baud rate formula, baud rate is equal to 2 raised to s mod into oscillator frequency divided by 32 into 12 into 256 minus TH1. So from this formula, you all can get an indication. What is this TH1? Right? We had seen timers earlier. So TH1 is that 8-bit higher register of timer 1. So that is an indirect indication. During serial communication, we will be using timer 1. Correct? And look into what it is done. 256 minus TH1. Mean that's again an indication because something is getting subtracted from the highest count, 256. 256 mean it's an 8-bit timer counter. Correct? So during serial communication, we will also require timer 1 operated in mode 2, 8-bit auto reload mode. For what purpose? For generating that baud rate, for generating a fixed frequency square wave. Is that fine? And another bit 2 raised to s mod. S mod is one of the bit available in power control register PCON. See here, there is a diagram shown for PCON. The last bit in PCON register, that is PCON.7, you have that bit s mod. On reset, that is by default, s mod bit is 0. It means during calculations, we will be having 2 raised to 0. Whereas with the help of instruction, we can set the s mod bit. Then it will be 2 raised to 1. Okay, so this is the relation for finding the baud rate. Is that okay? Now generally what happens is, baud rate is known to you all. Oscillator frequency will also be given 11.0592 megahertz, right? S mod, we will be either setting it or clearing it. Right? So with this information, we will be finding out what is the count that is going to be loaded in TH1 register. Is that okay? So in case of TH1 register, say we will look into some calculations for TH1 register if I know the baud rate. Is that okay? But before going to that, let us look into that power control register, PCON register. So the 7th bit in PCON, that is the last bit in PCON, is meant for serial communication, S mod bit. Okay, and look at the lower side, PCON.0, that is an idle bit. The next, power down mode, right? So idle mode and power down mode are used for reducing the power dissipation in microcontrollers, right? We had seen the explanation of PCON register in the earlier lectures. Whenever that bit is 1, suppose idle mode PCON.0 bit is 1, it means microcontroller is in idle mode. What is idle mode? Idle mode is CPU stops working, whereas the other peripheral circuitry and the other registers are active. Right? Idle mode is CPU stops working. When CPU stops working, it means there is no execution going on, there is no data transfer going on. So whenever there is no data transfer, mean there is no logic 0, logic 1 flowing in the circuit, mean there is no current flow, mean there will be no power dissipation or lesser power dissipation. So that is what is idle mode. Right? And in case of power down mode, the clock is completely stopped. Correct? Whatever crystal oscillator we will be connecting, it provides the clock to the internal circuitry of microcontroller, and the internal circuitry of microcontroller is sequential. So if we stop the clock, it means the entire circuit internally stops working. There is no logic 0, logic 1 flowing in any of the circuit. Mean there is no current flowing in the circuit. It means there is no power dissipation in the circuit. So that's the difference between power down mode and the idle mode. Okay. Now, to come out of power down mode, we compulsory need to reset microcontroller. And once we reset microcontroller, then you all know what are the states of SFR registers on reset. Right? So to come out of the power down mode, we need to reset, and hence majority of the special function registers are cleared. All the ports will have logic 1. Program counter is also cleared. Stack pointer is initialized to 7. Right? Mean the SFR registers change. Whereas in case of idle mode, how do we come out of idle mode? With the help of interrupt. Right? On arrival of any interrupt, microcontroller comes out of the idle mode and starts functioning from where it had stopped. Is that okay? And there is another way also by resetting microcontroller. But when you reset microcontroller, the special function registers are going to change. Is that okay? So in power down mode, compulsory special function registers are going to change whatever is stored in it. Whereas in case of idle mode, the contents of the special function registers as well as memory remain the same. Okay. And then these two are the general purpose flags, GF1, GF0. User defined general purpose flags. Right? Just to revise. We are dealing with serial communication. So what are we interested in? The SMOD bit of the PCON register. The last bit of PCON register. Is that okay? Now let us see if I know the baud rate, right? How to find out that count which is to be loaded in TH1 register, right? So let us go for count calculations for serial communication. And one example taken is if the baud rate is 9600 and by default that SMOD bit is 0. All the special function registers are cleared on resetting microcontroller. So let us assume SMOD is 0 and I know the baud rate. I know the oscillator frequency which is 11.0592 megahertz. Now on substituting these values, we will find out what is the count to be loaded in the timer 1 higher register TH1. So let us begin with the formula. Baud rate is equal to 2 raised to S mod into the oscillator frequency divided by 32 into 12 into 256 minus TH1. How much is the baud rate? 9600. What is S mod? That bit is 0. So we have 2 raised to 0. Oscillator frequency 11.0592 megahertz. So into 10 raised to 6. Now see here students, this is the exact frequency that you should be taking. Do not round it up. Do not take it as 12 megahertz. Right? If you take it as 12 megahertz, you will see that the count calculations will come in fractions, which will affect the square wave generated by the timer. Mean the baud rate will be getting affected. Right? There will be error in generating the square wave which is used for serial communication. So always use 11.0592 megahertz frequency while doing the count calculations in serial communication. Fine. Now on substituting these values, you will get, and just rearranging the equation, I'll be getting it as 256 minus TH1 is equal to 3. So TH1 comes as 253, converting it into hexadecimal. So that is FD hex. So for 9600 baud rate with 11.0592 megahertz oscillator, I need to load a count FD hex in TH1 register. Are you getting me? And the bit S mod is 0. Now what if that S mod is 1? See here, for the same baud rate, for the same oscillator frequency, I am changing that S mod bit to 1. So what are the count calculations? Now that S mod bit is 1 mean in the calculations I will have 2 raised to 1. So when I do those calculations, 9600 is the baud rate, S mod is 1, so it is 2 raised to 1. Oscillator frequency 11.0592 megahertz. And from that, if I go on solving it, what is TH1? It is 250. Mean the count that should be loaded in TH1 is FA hex. Is that okay? So that S mod bit, whether it is 0 or whether it is 1, right? By default, we take it as 0. Right? But in exam, look into what has been told. Right? Whether the S mod bit is set or not set. If it is nothing mentioned, we generally go for S mod is equal to 0. So that's how for serial communication, whenever you want to perform serial communication, the first thing that you should find out is, for this particular baud rate, for the given oscillator frequency, what is the count that should be loaded in the TH1 register? Is that okay? Now the next, when I say that S mod bit is going to change the calculation, so let us look into if that S mod bit is 0 and if that S mod bit is 1, how it is going to affect. Change it. Okay, so if S mod bit is 1. Okay, so depending on that equation, right, baud rate equation, we find out the various counts that are going to be loaded. Now see here, I have shown one table for that particular count, FD, FA, these are the counts for various baud rates, right? And now if S mod bit is 0 and if S mod bit is 1, what is it going to happen to the baud rate is what we will see in this slide. Right? So recently we calculated that FD, right? For 9600 baud rate, when S mod is 0, the count came as FD. Now if I load the same count, FD hex, and if I set the S mod bit, then what happens is I get the baud rate of 19200. Correct. So with this FD count, S mod bit 0, the baud rate is 9600, and if I set S mod, I get double the baud rate. That is what I want to tell you all. Right. So that S mod bit, look into the next FA hex. If the baud rate is 4800 and the S mod bit is 0, the count calculation comes as FA. And with the same count calculation, right, FA hex, I set that S mod bit. What do I get the baud rate? I get the double of it. So initially it was 4800 when S mod is 0. For the same count, on setting the S mod bit, the baud rate doubles. Is that okay? Okay, I'll just explain it in some another way. Okay. Now see here, I have shown a table for various baud rates. What are the count calculations when S mod is 0 and when S mod is 1? So let us look into the middle column. When S mod is 0 and the baud rate is 9600, the count calculation comes as FD hex. When S mod is 0 and the baud rate is 4800, the count calculation comes as FA hex. For 2400 baud rate, S mod is 0, the count calculation comes as F4 hex. And for 1200 baud rate, the count calculation comes as E8 hex. Now, if I keep this count FD hex and I set S mod bit, the baud rate available to me is 19200. Correct. So with FD hex, if FD hex is the count and S mod bit is set, I now find what is the baud rate that I get. And the baud rate that I get is 19200. With FA hex count, the baud rate achieved is 9600. We are looking into the last column. With F4 hex count, the baud rate achieved is 4800. And with E8 hex count, the baud rate achieved is 2400. So can you find the difference here? When S mod is 1, when S mod is 0, I have these count calculations, and if I do S mod, if I set S mod, I get double the baud rate for the same counts. Double of 9600 is 19200. Double of 4800 is 9600. Is that okay? So that's how that S mod bit affects the baud rate. Okay. Now now see here students, as I told you all, while calculating the baud rate, that TH1 register was there in the equation. It means I need to make use of timer 1 in mode 2. Correct. So while doing serial communication, I need to initialize SCON register, serial control register, as well as I need to initialize tmod register. And tmod register initialization will be what? We will be using timer 1 in mode 2, whereas timer 0 is not in use. For serial communication, it is compulsory timer 1 used in mode 2, right? So the gate bit will be 0. Okay, the gate bit will be 0. We will be operating in timer mode, so C/T bar will be 0 and the mode is 2, so 1 0. Whereas timer 0, we are not using it. They are don't care. We generally keep it as 0 0 0 0. So the tmod, I need to initialize tmod register also when we do serial communication. And what is the control word in tmod? It is 20 hex. Is that okay, students? Right? And then I need to start the timer. Right? I need not stop it because it is in auto reload mode, as we saw it in the earlier lectures. If I want some operation to happen continuous, we keep it in mode 2, which is auto reload, and we do not stop the timer. But I need tcon register to start the timer, right? And why are we using timer? So as to generate a square wave which will give the desired baud rate. Is that okay? Now let us see one example. The control word generation, SCON control word for reception and for transmission. Now whatever modes we saw, right? Mode 0, mode 1, mode 2, mode 3. Mode 0 is synchronous serial communication. Mode 1 is 8-bit UART variable baud rate. Mode 2, mode 3 is 9-bit UART with fixed baud rate, and the last mode 3 is with variable baud rate. We usually go for 8-bit UART with a variable baud rate. Is that okay? So let us see what is that SCON control word. If I'm going to go for 8-bit UART serial communication with a variable baud rate. First I will find the control word for transmission, and then I will find the control word for reception. Okay. Now this is the SCON control word. RI, TI, RB8, TB8 are the 9 bits. REN is the receiver enable. SM2 multiprocessor communication, and SM0, SM1 are the mode control bits. Now I want look into 8-bit UART. 8-bit UART mean which mode it is, right? It is mode 1. 8-bit UART with variable baud rate mean it is mode 1. So SM0, SM1 will be 0 1. Correct? So let us start from that MSB side, the bit 7 and the bit 6. It will be 0 1. SM2 is a multiprocessor communication. No, I am not doing multiprocessor communication. So SM2 bit will be 0. While doing reception, REN will be receiver enable will be set. During transmission, this bit will be kept 0 during transmission. Next, 8-bit UART means TB8 and RB8 are not into use. So again these two bits will be 0 0. And TI and RI are the flag bits. Whether that bits are set or cleared, we will get it automatically when that operation is either completed or going on. So TI and RI is available from the internal hardware. Whereas the other bits, bit 2 to bit 7, the user or the programmer will be setting it or clearing it. So let us see what is the control word, SCON control word for transmission. Correct? So for transmission, how the transmission is? 8-bit UART variable baud rate. So see here, SM0, SM1 that is 0 1. 8-bit UART variable baud rate mean mode 1. It's a single processor communication. So SM2 bit is 0. We are transmitting it so that REN bit is 0. It's an 8-bit communication. So TB8 and RB8 are not into use. 0 0. And these are the flags. TIRI will be set automatically by the internal hardware. So see what is the control word whenever we go for transmission, serial transmission. The control word comes as 40 hex. 0100 is 4 and 000. So for transmission, 8-bit UART variable baud rate, and this is what we normally prefer. Mode 1 is the preferred mode for serial communication. Right? So for transmission, the control word is 40 hex. And now for reception, again 8-bit UART variable baud rate, but now it is a reception. So see what will be the control word. So mode 1 is 01. It's a single processor communication. So SM2 bit is 0. Now it is going to be reception. So that reception should be enabled. So that SCON.4 bit is set. Correct. So that bit is 1. Whereas TB8, RB8, ignore because we are doing 8-bit communication, and TIRI are the flags. So the control word for reception is 50 hex. Is that okay? So please remember this, students. For transmission, usually mode 1 is preferred, and accordingly the control word comes as 40 hex. For reception, again mode 1 is preferred, variable baud rate, 8-bit UART, but the receiver should be enabled with the help of SCON, and hence the control word comes as 50 hex. Right? So that's how we generate the control word during serial transmission, which is required for serial transmission and which is required for serial reception. Hope you all are getting this, students. Okay. So now let us look into what is that multiprocessor communication. So we will see how that multiprocessor communication is carried out. Now multiprocessor communication means in a system there are more than one microcontrollers. So the diagram that you see here, you have one master 8051, one master microcontroller, and the other two microcontrollers shown here are the slaves. Such you can have many. Is that okay? So that's shown here, 8051 slave 1, 8051 slave 2. So something like this is called as multiprocessor communication. Okay. Now, to activate multiprocessor communication, the SM2 bit in SCON should be set. Right? And then, since it is a master and the other one is a slave, master will be transmitting data. So it is the TXD pin which will be used by the master, and the remaining microcontrollers will be receiving the data. So TXD of master microcontroller will be connected to all RXDs, right? The receiver pins of all the slaves, RXD of all the slaves. Okay. And now how does the communication happen? A multiprocessor communication. See here. While during the start of the communication, the master as well as slaves will set the SM2 bit. So SM2 bit of the master will be set, as well as the SM2 bits of the slaves will also be set. Then the master will send address of the slave. So the transmission begins with master will first send the slave address, and this slave address will be received by all the slaves. If there are 10 slaves connected, the address will be received by all the slaves. Again, the address is also sent serially. Okay. So the first step is the SM2 bits of the master as well as slaves are set. Second step, master sends the address, and all these addresses are received by all the slaves. Third step is whichever slave matches whatever master has sent the address, if that address matches with that particular slave, then that slave will clear its SM2 bit. On address matching, that particular slave will clear its own SM2 bit, and then master will automatically start sending data bytes. Initially the address was sent, the particular slave got activated, that slave cleared its SM2 bit, and now the master started sending the data bits. Whosoever slave's SM2 bit is 0 automatically starts receiving the data bits, whereas the other slaves, the SM2 bit is still 1. So they will ignore the data bits. Correct. So the slave whose address was identified, whose address was matching, and whose SM2 bit was 0 will start receiving the data bits. And that's how the data transmission happens. So that is called multiprocessor communication. Is that okay? Now, whether the master is sending an address or whether the master is sending an data, that is indicated by the 9th bit. While preparing the UART frame, master will set the 9th bit indicating it's an address. Correct? And while sending the data, master will clear the 9th bit indicating it is now sending the data. Fine. And always remember, multiprocessor communication always happens in mode 2 and mode 3. 9-bit UART. Correct? So multiprocessor communication is always a 9-bit UART communication, where the 9th bit, if it is 1, that's an indication address is being sent. And if the 9th bit is 0, that's an indication data is being sent. Correct? 8-bit multiprocessor UART is not possible. Is that okay, students? So that's how multiprocessor communication happens. Right? Now let us look into the serial data transfer program, students. Hope whatever is being explained has been understood. Right? So just a quick revision. We saw SCON register. Then the data to be loaded is in SBUF. While doing serial transmission, we also need a timer. Which one? Timer 1 in mode 2. So we need TMOD register also, and we need the run bit of TCON register. We have that baud rate calculation, the baud rate formula, right? So with the available baud rate, we need to do those count calculations. Is that okay? And with all this, basic knowledge, we will see how to write a program to transmit data serially and how to write a program to receive data serially using 8051 microcontroller TXD RSD pins. Right? So let us go for the first program. Let us read the statement. See here, students. So let us read the statement. Write a program to transmit some string is given. So into double quotes, I have put what are the characters to be sent, FAMT. So it's a string of 4 characters. Okay. So write a program to transmit FAMT string on TXD pin of microcontroller with 9600 baud rate. The baud rate is given to you all. At what rate the data transmission should be? 9600 baud rate. Assume oscillator frequency as 11.0592 megahertz. So I need to write a serial transmit program. What is given? The baud rate 9600. While doing serial transmission, microcontroller will send an 8-bit ASCII code for letter F. Then it will send an 8-bit ASCII code for letter A and so on. So that's how the characters will be sent. Is that okay? So now let us see how should we be writing the program. With the statement given, we know 9600 baud rate and we know the oscillator frequency. So from this, the first thing that we need to do is calculate the count that is to be loaded in TH1 register. So the first step that we should do is this. Count calculations for the required baud rate. Then we need to find out what is the control word for which is to be loaded in SCON register. Right? And as I said, these FAMT, there will be 8-bit ASCII code for it. And the baud rate is given to you, it's a variable baud rate. So 8-bit UART, and how is the baud rate, which it is decided by the programmer, and hence it is a variable baud rate. We should keep microcontroller in mode 1 serial communication. So accordingly, we should find the control word for SCON. Then we should find the control word for TMOD, timer 1, mode 2. After doing all these initializations, we will start the timer. After starting the timer, internally the baud rate or the square wave will be generated, and now we are ready for transmitting the character. Now how does transmission begin? As soon as we load the character in SBUF register, the transmission begins. So after starting the timer, we need to load the character in SBUF. Right? As we load the character, so for the first character F, mean the ASCII code of letter F should be loaded in SBUF. As soon as we load it in SBUF, one by one on that TXD pin. First the start bit, then the D0 bit, D1 bit, and so on. It will go on till D7th bit and the stop bit. Okay. So after loading the character in SBUF, we should keep on checking whether the transmission is completed or not. It means whether all the 8 bits of that ASCII code are transmitted or not. So we will keep on checking the TI flag, transmission interrupt flag. If the TI flag is 0, it means the transmission is still going on. We should wait till the transmission ends. So we will keep on checking the TI flag. Right. So TI flag is 0, mean microcontroller is busy transmitting, wait. As soon as the TI flag is 1, mean the transmission is completed. So we will clear the TI flag and then we will go for sending the next character A. Right. How do we send the character? By loading the character in SBUF. Is that okay? So we will keep on repeating. See here, students, we will keep on repeating steps 5 to 7 till all the characters are sent. After A, we will be sending M and then we will be sending T. So this is the logic of the program or the algorithm of the program. Is it okay? So see here, always whatever problem statement is given, we are going to do transmission. So the first thing is, for the given baud rate, find out the count, initialize SCON control word, initialize TMOD control word, start the timer, load the character in SBUF, and keep on checking the TI flag. That's how will be the logic of our program. So now let us go for the program. Let us go for the calculations first. Right. So we had seen this before. So count calculations, 9600 baud rate. I am assuming S mod as 0 and the oscillator frequency 11.0592 megahertz. So with all the known values, baud rate, S mod, F oscillator, we find out TH1. And the calculation for count calculation for TH1 comes as FD hex. So this is the count that we will be loading in TH1 register. Now let us go for the next. Right. Now once we have calculated the count, now we will go for initializing the control words. Right. So what is the first thing that we did is we calculated the count. So count loaded in TH1 is FD hex. The second thing that we will do is SCON. So what is the control word for transmitting data? We have just seen few minutes back. For transmission, the SCON control word is 40 hex. That is mode 1 8-bit UART and a variable baud rate. That is mode 1. And during mode 1, the control word for transmission is 40 hex. For reception, it is mode 1 8-bit UART variable baud rate. The control word is 50 hex. Now we are doing transmission. So SCON control word will come as 40 hex. Then what is the TMOD control word? Timer 1 mode 2. So that control word comes as 20 hex. Right. Then we will start the timer. How do we start timer 1? We will be setting the run bit TR1. Correct. Next, how the transmission begins? By loading the character in SBUF. So the instruction that you will be using is MOV SBUF comma. Now SBUF is a special function register. Correct. All addressing modes are possible. Either refer the SFR by its name or by its address. So the possible addressing mode is SBUF comma hash, that is immediate addressing mode, direct comma direct, or direct comma accumulator. So I will prefer to use MOV SBUF comma A, where data or the character from accumulator should be transmitted in SBUF. So that's how we will be loading the character in SBUF. Okay, we will be loading the character in SBUF. Now see here students, we need to be careful. This is the character which is to be transmitted. So I should know where are the characters stored. Are they stored in program memory? Are they stored in RAM memory? Okay, so for our program, let us assume these characters are stored in program memory. So from program memory, we need to copy the character in accumulator, and from accumulator, the character should be loaded in SBUF. Is that okay? So that is how we will be loading the character in SBUF. Now, as soon as the character is loaded, the transmission will begin. Okay. Now we will keep on checking the TI flag. Check the transmission interrupt flag. If the flag is 0, we will wait. Let the transmission be over. So how do we do that checking? Jump if the bit is not set. TI is 0 mean the bit is not set. So jump if the bit is not set is the instruction we will use. Which bit are we checking? TI. And we will give some label. Right? And we will keep on continuously checking, is the bit set, is the bit set, or is the bit not set. So this is the instruction we will use to check the flag, JNB. Now, as soon as the flag is set, I mean the transmission is over, we will clear the TI flag and we will repeat the steps 5 to 7. Is that okay? Now, since the timer 1 is in auto reload mode, we need not stop the timers. That is internally used to generate a square wave with the desired frequency so as to get the desired baud rate. Right? So we need not start and stop. Once the timer is started, we do not stop it. What we only do is whether the transmission or the reception is completed or not is what we keep on checking. So that's why we keep on repeating steps 5, 6, 7 till all the characters are sent. Right? So with this basic information, with this understanding, let us write the program. Correct? Now, I'll start writing the program. Right? Please keep in mind what do we do? We need to load the count in TH1. We need to write SCON register, TMOD register, and we said where are the characters FAMT, where it is stored in program memory. So this is our assumption. Okay, it's nothing mentioned in the problem statement. So we have assumed it. Let the characters be stored in program memory. So data is to be picked up from program memory. Mean I have to make use of the instruction MOVC A comma @ A plus DPTR. Correct? It means I need to initialize DPTR pointer with the starting address of that FAMT array. Correct? Now, how many such characters are to be sent? See, whenever we write SBUF, one character will be sent. Such I need to send 4 characters. So I need to repeat this loading in SBUF, transmitting, loading in SBUF, transmitting 4 times. So I need a counter which is loaded with characters, 4 characters. Okay, so with all this in mind, we will start with our program. So ORG00, sjump next, and this is from where we start, label next. So what is the first instruction that we need to do? Storing the starting address of our array in DPTR register. So MOV DPTR comma hash 100 hex. This is our assumption. At 100 hex location onwards, the characters are stored one by one. F, A, at 101 is A, at 102, M, at 103, T, F, A, M, T. Okay. So we are loading the starting address of the array in DPTR register. Then we are loading a counter, MOV R2, 4 characters are to be transmitted. Correct? Next, we will load the count. So MOV TH1, FD hex, that was the baud rate count calculation. Then we will initialize the TMOD register. So MOV TMOD, hash 20 hex. That is type 1, mode 2. Then we will initialize SCON register. Transmission, the control word is 40 hex. Correct. and then we will start the timer. Is that okay? We will start the timer. That is set the run bit. Now, as soon as we start the timer, we can begin the transmission. So we will load the character in SBUF. Now, where is the character? In program memory. From program memory, take it in accumulator. Take the character in accumulator, and from accumulator, load the character in SBUF. So data transfer from program memory, the instruction is MOVC A comma at the rate A plus DPTR. So DPTR is 100. 100 hex mean it is pointing to the correct character, correct address. It is having the correct address of the character. So nothing should be added. A plus DPTR mean before writing this instruction, we should have cleared accumulator, CLRA, and then pick the data from the memory location 100 hex, MOVC A comma at the rate A plus DPTR. And now the character is in A, the first character is in accumulator, that character F. So whatever character in accumulator is, store it in SBUF. So MOV SBUF comma A. And as soon as we load the character, the transmission begins. So we keep on checking the flag then, TI. If the TI flag is 0, jump if the bit is not. Where to jump? At the same instruction. Keep on continuously checking. Okay, keep on continuously checking the flag bit. As soon as TI flag is set, in the transmission is completed. So clear the transmission flag. Right. So as soon as the TI flag is set, clear the TI flag. Okay. Now one character has been sent. So decrement the counter. Right. Such we have to send 3 more characters. Right. So one character has been sent. That character F has been sent. Now we need to decrement the counter. Right. DJ and Z R2, because that R2 keeps the track of how many characters are sent. And then we need to repeat the process. Take the next character in accumulator, send it on SBUF, keep on checking the flag. Correct. But now one character has been sent. Let us point to the next character. So pointing to next character mean we need to modify DPTR. So before decrementing the counter, what I need to do is I need to increment pointer. Let the pointer point to the next character. Then decrement the counter and then repeat the process. Take the second character in accumulator. So taking the character is done by MOVC A comma at the rate A plus DPTR. So before using accumulator, clear it, or else some random data in accumulator. Random data, in fact, the ASCII code is what is there currently. That will get added to the address. No, I do not want that, because DPTR is pointing to the correct address. So clear the accumulator and then pick the character pointed by DPTR in accumulator. So that second character comes in accumulator. Store it in SBUF and keep on checking the TI flag. As soon as the TI flag is set, mean even the second character has been sent. The ASCII code of second character has been sent. Clear that flag, point to the third character and repeat the process. And once all the 4 characters are been sent, we will come out of the DJNZ loop, correct? And we will end our program, sjump stop. Correct? So that's our transmission program. Okay. As I said, we have assumed that the characters are stored in program memory. So this is where we are writing the program. Mean that array should also be available in the program memory. Starting from which address? 100. So let me do that. Right? Let me give the array available at 100 hex. So org at 100, and I will store those. I'll store that string. Define byte, and then in double quotes I put the string FAMT. So this is where the string is available in program memory, is what we have assumed. Fine. And then we end the program. Is that okay, students? So just let me copy this program. Okay. And we will execute it and see. Okay, in Keel we will execute it and see. Okay, so let us begin with project new. So let us create one folder, serial transmission, right? So let me give the name serial TX as the name of the project, microchip 8089C51. Okay, let us select create hex file and let me paste the program that we had written. Okay, let me save the program. So serial tx.a. Okay, let me add the program in the workspace. Okay, let us check for syntax errors. So it is 0 error 0 warning. Now let us simulate the program. Right, so this is your program. Now let us see that memory. See where we have stored the characters at code memory. So let us take memory window and it is code memory. So C:0x100. At this location we have stored FAMT. So can you see that FAMT character F, the ASCII code is 46 in hexadecimal. A, the ASCII code is 41. M, the ASCII code is 4D. And T, the ASCII code is 45. So we have loaded the string in double quotes, but while storing it, right, the ASCII codes are stored in the memory, and these are 8-bit ASCII code for each character. Okay, so when we execute our program, we will see this ASCII code, right? We will be sending this ASCII code. Is that okay? Now, what we can do is, we will see while executing this program, we will see this ASCII code getting loaded in SBUF, and when the ASCII code is transmitted, that TI flag will be set, is what we will see. Using that peripheral window, see your students, using the peripheral window, I have selected the serial communication register. So all the details related to serial communication. And one more thing, for serial transmission, I will be selecting UART window, serial window. Like see, you all had memory window. Similarly, I have for serial communication a serial window. So go to view and look at the downside, memory window, and below it you have serial windows. UART1, UART2, UART3. So let me select the first one, UART1. Now, can you all see the change? Right hand side at the down, that UART window is visible to you all. Okay. Now, whatever we transmit, that transmission happens on the TXD pin will be shown on this UART window. Okay, students. So I run the program, that is burst execution. And what am I transmitting? FAMT. That FAMT should appear in that UART window. Right hand side, down corner. So I am running the program. See burst execution. I run the program. And can you see FAMT? Can you see this? Okay. If you have missed it, let me stop the program. Let me come out of the debug session. Okay. Again, I enter into debug session. Right. That UART window is automatically selected. I hope you all are able to see that UART window. Now see that UART window is blank. Hope this is visible, students, that UART window is blank. And now I run the program and I will see FAMT characters in the UART window. So let me run it. Are you able to see that FAMT? Right. So that's how it means our program is working. And that's the program for serial communication, serial transfer, serial transmission. Okay, students. If any doubts you all have, students, or please write a comment in whatever video lectures I post. Okay. So thank you for attending, students, and see you in the next session. Bye, students. Bye.